Okay, so if we can, it is good to continue. So
Okay.
can I continue? So now what I'm going to do, I'm going to solve that problem, and I'm going to solve it again in a very conceptual way, which is in fact interact with what we just discussed with Bish. But first of all, let me finish with this. So now we have P infinity, we have P1, and we have this relation on the boundary for P1 and P infinity. Now, how I perform them? Well, first of all, it is, by the way, it is a temporary. Of course, to make this small, I have to have real part of beta less than 1/2. So it appears, of course, because of this, you see, I have to move this and cancel that, and zeta contains n. So so this I have just n, but n beta it is here. So when I just move it to cancel those two, I arrive to this beta. But this is actually a technical stuff. It can be, I can get rid of it, but I won't. I just assume this. So this is a small and now I construct the last step, construct the matrix R with them. So far everything is explicit. It is not, although there is this relation, there is no asymptotics here. So it is just the explicit transformation. So now I'm going to go from S to R and to construct function for which I would have jump matrix close to identity. How I do it? In a very natural way. I take S and divide by P1 in U. I take S and divide by P infinity outside of U. And this would mean this division. But this function R would not have any jumps inside U because they are cancels. And outside of U, it would not have any jumps on the unit circle because again it cancels. So what is the jumps for R? It is this. It is those pieces of gamma 1 where jump is exponentially close to identity, and across the unit, across the circle, across the boundary of U. Here it is just the division, P infinity and P minus 1. And because of that relation, it is also close to identity. Not exponentially, but like 1 over n. Well, then it is as I said, so I got a Riemann-Hilbert problem where the jump matrix is uniformly close to identity. So the R itself is uniformly close to identity with this error. That's it. So this would be the end of the leading terms of symptotic analysis for my solution of Riemann-Hilbert problem in Fisher-Hartwig situation. Now what and indeed as Professor Lyalinov said, we could have stopped here. Okay, Phi3 is described as a model problem, but this is a great bonus. In fact, we can solve it in contour integrals. How? And now this is the tricks which people who were born in integrable systems, of course, would realize immediately what I'm doing now. So I continue undressing my Riemann-Hilbert problem. I go from Phi3 to psi function just to incorporate inside this exponent, which I did when I checked the behavior at 0. And now what can I say about function psi? Function psi, its jumps already constant. So this incorporation, this factor actually kills all dependence on zeta in jump matrices. But of course, it would appear at infinity. So I have a function psi, which has constant, which is analytic outside of this gamma. It has constant jumps, and it behaves as at infinity as it has this essential singularity at infinity, and it has this behavior, this branching, this branching behavior, power-like behavior at 0. Well, everything is constant. C is also constant. Now well, so in our case, of course, C1, C2 are given. But what I'm going now to do, I'm going to think about this psi, again, taking this philosophy of Lyalinov, taking this psi as a function of C1, C2. It is a function that is defined by this setting with C1, C2 as a free parameters. So this is a specification for my purpose. But in principle, I now want to look at this Riemann-Hilbert problem as just parameterized by two parameters. Alpha, beta are fixed for everything, forever, and C1, C2 are free parameters. They're not exactly free. You remember we had this condition on A on A on previous A that its eigenvalues are plus minus e to the 2 pi I. So trace is this. So in any case, for any S's, not only for this one, to make this problem well posed, I have to have S1, S2 satisfy this relation. It is just the trace of A. This is the only, with this condition, this would be well posed problem. I would be able to find C's. And my concrete C's, S's satisfy this condition. But let's, for the time being, forget about this concrete, and let's think about this psi as a something which is defined by C1, S1, S2. And again, it's going to be a miracle. For any S1, S2, I will be able to write this psi explicitly. That's the point. And in particular, of course, for my concrete C1, C2, which would lead to the solution of my problem. Okay, now the kind of the main claim. So again, for the people from integrable system, this is sort of obvious. You have a Riemann-Hilbert problem with some essential behavior at infinity, with some branching at some point, and all the defects from the analyticity are constant. So all the jumps, all those functions C's are constant. It means this function should satisfy the linear system of this type when A not some 2 by 2 matrix independent on Z. Why? So it is again the standard thing. Let me consider this logarithmic derivative. So psi satisfies that Riemann-Hilbert. Let me consider this logarithmic derivative. So the key point is that although psi jumps, A does not, because you have not differentiate jump matrix. So this jump matrix just would cancel. And so A is, it continues over jump contour. So it means that A is analytic everywhere outside of zero. So this is so A is an analytic function on C minus 0. By the way, why I can write inverse without any problem? Because of course determinant psi is 1. It is just if you write determinant psi, determinant would not have jumps. It would not have. It everywhere would be 1. Okay. So to find what is going on, it means at 0, I have to see what is going on with this logarithmic derivative at 0 at infinity. So what is going on at infinity? I can, by the way, I can differentiate everything. This can be proven kind of independently. So AZ, when I differentiate, so my psi, I write psi in more details. I just specify this first residue part, M1 over zeta. So this is a derivative. So this is A, this is a derivative of psi up to the, I don't need to differentiate this one because it would be already too small. So this is the derivative of this thing and multiply by psi minus 1. So this is the principal part at infinity, just this function and then decay, which can be actually write more specifically 1 over zeta C terms can be write like that. Easy. What is going on at 0? At 0, it is the leading term. The principal part is this. Again, I just put this representation, this behavior at 0. C, I don't need to differentiate C's. C's are constant. And so it would give me this expansion for A at 0. So it is a pole. No, that's it. So it means that my function A It is a sum of its principal parts. And moreover, for A naught, I can either describe it in this way, or it is from the expansion of 0, or like that from expansion at infinity. In any case, it means that in particular from here, I see the diagonal part of A is minus beta beta, because this thing does not have diagonal part. And off diagonal part, it is the off diagonal element of M1. Or also, there is a relation, and they are not totally independent P and C, because from here, I see that the determinant of A naught is alpha squared, minus alpha squared. So, and this is a condition. So it means having S1, S2, I can construct a linear system with matrix A, which is parameterized by BC, which is related by a condition. So I have, you gave me S1, S2, I produced linear system parameterized by B and C. So far, there is no any explicit formulas, of course. It is just so, and I actually want to discuss, I want to have this map explicitly. Well, again, it would be great bonus. So it means that what we have now, it is that we want to discuss the kind of inverse and direct map between B and C, which parameterizes this linear system, and C1, C2, which parameterizes Riemann-Hilbert problem, which yields this linear system. Now, to discuss this map, it is good to change temporarily point of view. Let's now take this system as a principal object. So I want to take this system as a principal object, apply. So this is the way how I'm going to reach my goal to solve explicitly my Riemann-Hilbert problem. So now after this claim, after seeing that solution of the Riemann-Hilbert problem satisfies this equation, I came to the following idea: how can I solve my Riemann-Hilbert problem? The idea is this. Let us just look at this equation from the point of view of theory of system of linear ordinary differential equation with rational coefficients, and let us use ingredient of the theory to solve my Riemann-Hilbert problem. Or first of all, to identify what does my Riemann-Hilbert problem mean from the point of view of the classical ingredients of the Monodryme theory to this system. Okay, so let me just formulate the absolutely classical facts which I should consider when I'm given a linear system. So this linear system has one irregular singularity at infinity and one regular singularity at 0. This is just, I begin to use terminology of the end of 19th century. So this is what we can say about this system. Moreover, so we can how can we describe what is going on around irregular singularity at infinity? Well, there are canonical solutions. So the point is that you can just formally check that this sort of series, of course, it is the same as a series in my Riemann-Hilbert problem, but now I kind of don't think about Riemann-Hilbert problem. It is just the fact of the theory of differential equations. This series would satisfy this equation with the proper choice, and for all M1, M2, I would get explicit recurrence relation in terms of A naught. So this behavior, most importantly, it is this behavior which is dictated by this term in my linear system, of course. Now again, from the general theory, we know that generally you cannot have functions which has this behavior, this asymptotic behavior everywhere around infinity. You have to have sectors. And because of the Poincare rank 1, you have just 3 sectors. First sector, it is you just threw away up positive imaginary part. So you have only one oscillatory ray here. It is, you can guarantee existence of this solution, psi1, with such behavior. Then you have sector 2, and then you again you threw away negative imaginary part. And then you would have sector 3. It is more or less the previous sector, but on the other sheet of universal covering. And there is a relation between psi3 and psi1, because actually psi1 and psi3, they are almost the same up to the, because we have this branch at infinity. Very good. So this is what is going on at infinity. This is a local behavior, local theory at infinity. What is going on at 0? At 0, we have regular singularity. It means that there is a solution which is up to the golomorphic left factor is this branching function, is this multiple for this power function. Now, what are the Monodrama data of the system? First of all, it is a Stokes matrices, relation between canonical solution at infinity. Psi2 equals psi1 times S1, because it is a solution of the same equation. So there is a right multiple constant matrix. Because in the right half plane, I can use the same asymptotics for both functions. And I get that S1 necessarily have to be of this type. But I cannot, of course, define S1. Then I have S2, which is between psi3 and psi2. And again, on the left half plane, it is a half plane when I can use in both functions the same asymptotics. And so I get S2 like that. It is another triangularity. It is, of course, the same matrix. It's almost, yeah. And finally, there is a matrix. It is our previous C1, which connects, say, psi2 and psi0. Those S1, S2, and C, they are not independent. There is the so-called cyclic relation, which can be, again, derived more or less as I derived a similar relation in the previous, in the previous hour. And it would yield this condition, which was, again, we had from our Riemann-Hilbert problem. Here, I arrived to this condition. I am not talking about Riemann-Hilbert problem yet. It is just the fact that I can calculate monodromy. I can take psi2 and kind of go around infinity, go around 0 in two ways, using the Stokes matrices or using this representation. Cyclic relation, it is called in monodromy theory. And it leads to the, first of all, it allows me to find C, and also it leads to the condition between S1 and S2, the same trace condition. So that's the facts of monodromy theory. Again, it is absolutely general. I just applied general ingredient of the general theory to this particular system. And again, I have not solved explicitly anything yet, but I can just take, but everything exists. So exists those canonical solutions, exists those S's, and I can construct solution psi, which corresponds to this S1, S2. So very simple. I just take psi to be equal to psi2 on the upper half plane, to be equal to psi3 on the left, on this quadrant, and to the equal psi1 on the right. And that's it. So this function would satisfy my psi Riemann-Hilbert problem with S1, S2. And look, again, I constructed my psi chi. They are kind of functions of B and C, functions of the coefficients of the system. They are solution. I construct them as the solution of differential equations. So they are functions of B and C. My psi originally, it is a solution of Riemann-Hilbert problem. So it is parameterized by S1, S2. Again, although it is not explicit, no explicit formulas yet, but this is a kind of theoretical parameterization. Canonical solution psi chi is given as a directly from the direct monodromy problem as a function of BC. Solution of the Riemann-Hilbert problem, it is a function of S1, S2. So to clinch, to use monodromy theory of this differential equation, I have to establish relation between BC and C1, C2. So, and again, in general setting, that would be all. So I would just only refer to the general inverse monodromy problem or direct monodromy problem and I could not say more about those functions. But, and this is a great bonus, key fact that psi k as a function of B and C can be found explicitly in terms of contour integrals. After that, you can solve everything. You can express everything. And now, why this is so? This is simple, but still, on my point of view, very mysterious fact. So I cannot see, the mystery is that I cannot see, at least I cannot see that this can be solved, that my system can be solved explicitly in terms of contour integrals. Thus, from the matrix form of this system, I cannot see it here from the matrix form. But if I do the very trivial thing, just go from the system. So this is I wrote that just the first column, system for the first column, and go to the second order differential equation for just one function, which is of course very simple idea. Just express psi21 in terms of psi1 and then substitute it to here. I would get just one equation of psi11. Then I make trivial, which is kind of the natural transformation, go from psi11 to W. Why I do it? Because this equation, I don't see, I still don't see that I can solve it, because it is the coefficients of these equations are quadratic function of zeta, of xi. So it is still formally. But if I do this change, but this change already can be predicted, I arrive to this equation for W, which is whose coefficients are linear functions of zeta. And now, of course, we all know that we can use Laplace method.
You say that this is mystic, but the same situation we have for nonlinear Schrödinger, for example.
No, but yes, but all this is, so you see, you can consider oscillatory Riemann-Hilbert problems. So what does it mean, oscillatory Riemann-Hilbert problems? Again, it is a functions which is Riemann-Hilbert problem posed on the race and having essential singularity at infinity. This essential singularity at infinity is governed by some polynomial. So e to the power of some polynomial. This is a kind of the degree of this polynomial. It is a Poincare rank. And the number of the race and their position is also dictated by this higher power of this polynomial. And so you can consider all the family of this oscillatory Riemann-Hilbert problems on the race. Moreover, you can of course write the jumps matrices. They all have to have this specific triangular structure to accommodate the exponential asymptotics. And so you have this collection. And now, indeed, it is always, for any polynomial in the essential singularity, it is always non-commutative. So you cannot do just trivial logarithm, taking trivial logarithm and solve it. But again, Volodya, the mystery. So if this polynomial is linear or quadratic, you can make this transformation to second order differential equation, which can be solved by Laplace method. If it is before, if it is beyond, if it is already cubic, then you cannot. At least it is not well, it is not a theorem, but it is kind of the Wojtasz's conjecture, if you like.
I see. I understand situation, but you have you say that mystic is the transform from the matrix equation
Yeah,
to.
this is strange. I cannot see it. So yeah. So why? So why cannot what? Okay, maybe I am just very ignorant. Maybe it is. Well, maybe there is such a thing as a matrix. Well, there is such a thing as a matrix Laplace transform, but I don't know. But I personally have no other means to show that this system has solution in the contour integrals unless I just reduce the system to the second order differential equation.
But of course, the first step that you should make in such situation is to transform this a matrix solution to a scalar solution.
No, yes, but why cannot I kind of do it directly? Anyway, so in a sense, yes, I still have some time. Yes, so this is I don't know how how much I managed to deliver, but this is the end of the so this is basically end of the story because I'm not going to torture you with all these long formulas with gamma functions, but yes, but so this is I can apply Laplace method, or which is not really that important. Of course, I can, because this is a system with very easily classified. Making this change of variables, I arrive to the standard confluence hypergeometric equation. But this is no worse than this one. So this is from the analytical point of view. It is just this is just have a name, it has a name and already a lot of concrete things done. But again, so in principle, it is a good to make connections with yet another classics. So those canonical solutions can be expressed in terms of the confluent hypergeometric functions. So that's end kind of the story up to the maybe tedious but very clear technicalities. We can do now everything, and we can obtain, so as I said, we can obtain S1, S2 explicitly in terms of, well, gamma functions involved in terms of BC explicitly gamma function involved in terms of S1, S2. And so indeed we have explicit formula for P1 in terms of my S1, S2 in terms of alpha, beta. And so we have asymptotics for my Y. Then there is, I don't have time for it. There is another important ingredient, because it is a asymptotics for Y. It means that I can immediately from Y extract the asymptotics for Hn, for the norms of my orthogonal polynomials. And so I would have asymptotics for the Toeplitz determinant, but up to the constant. So to get the constants, I have to work more. So I have actually to write a proper differential identity for my Toeplitz determinant with respect to alpha and beta. And so I would be able to arrive and kind of connect through these differential identities the alpha equals 0, so the Séguier case with my case. So this is yet another ingredient important, which actually also has a kind of the good name from the general theory of integrable systems. So my Toeplitz determinant, now I have this my Toeplitz determinant is a tau function of this monodromy system, and the derivative of Toeplitz determinant with the alpha beta, it is just the kind of the dependence of the tau functions on monodromy data. You can Google it and find several very good papers by Marco Bertola and his colleagues about exactly this issue. So it is, as I said, although it is very technical, but it is still every step in this thing is conceptual. So I just skipped steps which are not conceptual, just like here. So when I see that I can solve this by contour integrals, this is a conceptual step stop. So now it is just my my time, my efforts, usual technical efforts to work with contour integrals, with gamma functions, and with everything, which is still fun, of course. So now I still have, so what about if you, 15 minutes, 20 minutes?
Okay, okay. Of course.
Yeah, so,
Yeah.
yeah, so 9 plus 9 plus 2 is 11. Yes. Okay, so now let me just. So now the last portion, which is so that to justify the name of my lectures, Toeplitz determinant and Painlevé functions. So now it is a third situation. So we consider it SPbU case, SPbU, smooth symbols. Then we consider it a singular symbol. And now we consider transition from one to another. So this is where this is exactly. So this is a transitional asymptotics. Transitional asymptotics. It is where we have appearance of Painlevé. And again, more other generalization, higher order generalization. There we have where we have Painlevé. So again, if you have transition, it means you have some kind of double scaling limit, and you have some scaling parameter of this double scaling limit. And the Toeplitz determinant will be described in terms of Painlevé functions of this parameter, of this scaling parameter. So now let me be more precise. So I model the situation. This is our paper with Tom Claes and Igor Krasovsky. Well, there are many, I missed, of course, mentioned in my previous, there are a lot of course, references. Now, so this is a model. This is a family of weights, family of symbols that indeed kind of interpolate between SPbU and Fisher-Hartwig. So this is what? This is, I have this multi-valued function, which has, this is its branching point, which I denote as e to the t, e to the minus t. So this is this branching. This is a SPbU part, which and t is non-negative. So when t is strictly positive, then I have SPbU case. Then it is great symbol. Then it is great symbol. This, by the way, is the usual situation in application. And the analyticity in annulus, it is exactly the analyticity in annulus between these branching points. So this is analyticity in annulus. And it is if t is not 0. But if t is 0, those branching points, they collapse to 1.1, and it is my previous SPbU symbol, Fisher-Hartwig symbol. So what I'm going now to study, I am going to study the double scaling. N goes to infinity as before. It is in my Toeplitz determinant, but simultaneously t goes to 0. So ideally, I want to write kind of uniform asymptotics with respect to those two. But in the meantime, I would get asymptotics, so they will be express asymptotics in terms of, so the scaling parameter which I'm talking about, it is n times t. N times t is going to be first kept bounded, but then I will also allow it to go from 0 to infinity, so that I will indeed glue everything. So this is so let us now discuss. Let us now try to do exactly as we did before, especially that if t is not 0 yet, we have a situation with we have a SPbU situation. So we have precisely the SPbU situation. So I can just go from 1 to s, just I did for SPbU, and arrive to the picture which I had for SPbU case. A little bit deformed because I am now, you see, t will be close to 0. So those 2 points, they are close to each other. So my C, my gamma naught, my C, my gamma 1, they are begin to be close to each other near 1. Well, but before they are not, before t, until t is not exactly 0, there is still a room. There is still a way to pass. So this is again what we had before. This is a jump on the unit circle. This is the jumps of gamma naught. This is jumps of gamma 1. So now my first step, it is construct P infinity. And I'm going to construct again P infinity. Well, this time I'm just use exactly the sort of the Wiener-Hopf way to write this phi. So I split this phi onto 2 parts. So this is phi minus, this is phi plus. And I construct P infinity in this way, just like before, maybe different notations, but just like before. And so it was alphas in my first part, it was curl D in my second part, now it is phi plus, phi minus. So this is P infinity. And now, important difference. I am not now so to get the local, I am do this thing. So I am before going to the, so this is going to be good representation of my asymptotic representation of S if t is fixed, if t is positive and fixed. But if t goes to 0, it is not quite. So I have indeed go to some local problem, but the local problem now is going to be more sophisticated. So let us just, first of all, using this P infinity and get rid of unit circle. Just by this transformation. I could have done it in the, it is what I do in the, it is exactly what I do in the, almost what I do in the, okay. So what we have, so S tilde now would have jumps only on gamma, not gamma 1. And here it would have this. So you see my phi. So now it is phi minus phi over plus. So this is a difference. So this is this. I did not did it before. I did not use pi infinity in this way, but now I do, and this is what I get. And again, of course, this is a good exponentially decaying part, but it is outside of this now squeezing neighborhood. So now the point is that now I am going to, so now I am going to analyze, to see, to construct local Riemann-Hilbert problem just on this neighborhood, just on this neighborhood. To this end, and I want to simplify those matrices as much as I can in this small neighborhood, assuming that this is this. Okay, so to make things easy, let us forget about CGO part. It is easy to take into account later on. So I'm just I go to my variable zeta xi, and I write, but now I write my phi minus just explicitly in terms of nu. It is explicit formula. Now I would assume that my xi is still bounded, so it means that this is a squeezing neighborhood. So I can actually, so this is, I can rewrite this is okay, this in this way, and then I can rewrite this in this way, introducing. So you see, I just reduce to the common denominator and write it as xi plus x over 2 over n. And I assume those guys bounded. So this is a small small argument of exponential functions. So it can be roughly replaced by this. So it is a branching at x over 2. Similarly with phi plus, I do the same. This is again, and I arrive to the branching at minus x over 2. So this is a difference. So this is again, this is difficult to motivate this construction, difficult to avoid the jargon about indeed squeezing neighborhood, and anyway, so assuming that in my change zeta is bounded, it is indeed phi1, phi plus behaves like that. So it means that for the local problem phi, so now I'm going to the xi, I'm going to the xi plane, I would obtain the following. This is the parts of the gamma naught gamma 1. And this is what I have. It is difficult to see, but this is exponential function. And don't look on those guys, not important. But in the denominator, I have the product of this branching functions, of this multivariate, of these power functions. And here it is all the same power functions in the denominator, in the numerator. Okay. So now we are going to psi naught. I'm just undress this matrices with all those guys. I just take f naught and multiply by this exponent. It would take care of this e, and by these two logarithmic functions, it is power functions, which would take away those products. And so for psi naught, I get problem. So again, I want to arrive to the problem with constant jump matrices. This is what I'm doing. This is why I'm doing this. Because again, I want to arrive to something which I can write differential equation for. And so this is what I get. So this is a jump contours for my function psi naught. So it is now on those guys, it has only constant matrix psi, and I have price, I have just these jumps because it is because these functions have jumps around this race. So psi naught again at infinity as before, I can argue that it is what I have at infinity. Now there is no singularity at 0, but there are singularity at those 2 points. So this is a function, this is a model Riemann-Hilbert problem. This is a model Riemann-Hilbert problem in this transition situation. And you see, it is very important. Unlike my previous situation, unlike the Fisher-Hartwig, I have parameter. There were no parameter before. I have parameter. I have parameter x. Actually, I can of course move this x to the exponential behavior, just making a scaling of xi. But it is not a big deal. The point is I cannot get rid of this x, and this is of course essential. And the point is that it's very interesting that it is not a theorem, but already this problem with this 2 extra instead of one regular singularity with 2 regular singularity cannot be solved explicitly. And simultaneously it has a parameter, which my previous problem did not. So that I also find it is kind of suggestive that I begin, so I am able to solve explicitly my oscillatory Riemann-Hilbert problem only if I can get rid of all extra parameters by scaling, by everything. At the moment I cannot do it, I cannot solve it. But I cannot solve it, but I can study its behavior with respect to this parameter. This is a kind of the general ideology. Okay, so that is, we are almost done. I believe that you are tired and you did not probably follow well. Yes, and this is, but this is again the summary is that now in my so I would translate. I translate behavior of phi minus phi plus into this power function behavior near x over 2 minus x over 2. And now considering again this logarithmic derivative of psi naught, I would arrive to the, instead of the, in the previous case, I had a naught over zeta of xi. Now this 1 over xi kind of split it into 2 regular singularities. And in a sense, this is, and once again, I cannot solve, not a theorem, but I cannot solve this in contour integrals. But I can express those A plus, A minus in terms of solution of Painlevé 5. Why Painlevé 5? Because I can also differentiate psi naught with respect to x. And in this situation, which I did not have before, because I did not have any extra parameter. But now I have all my jump matrices do not depend on x. They not only don't depend on C, but they also don't depend on x. So it means I can differentiate with respect to x and get also rational functions. It's like this. And this is this. Just you look at the sum. There are now many several big survey and textbook on Painlevé equation. This is a Lax pair for Painlevé 5. This is a Lax pair for Painlevé 5. So A plus A minus would satisfy the function of x, would satisfy certain nonlinear differential equation, which are equivalent, which can be expressed equivalent to the equation of Painlevé 5. And that's it. So let me present the final answer. So the final answer.
You have not such a step at the previous calculations.
Huh?
You have not such a step at the previous calculation. You have not another differential equation.
No, because I don't have parameter.
Parameter. I see.
Yeah, that's the whole point. That's very interesting. So again, think about as I said, oscillatory Riemann-Hilbert problems. If you in your exponent which governs essential singularity, if it is quadratic, then by shifting lambda or z and scaling, you can get rid of all coefficients and get it e to the z squared. But if it is z cube, if it is cubic, you still would have at least one parameter. And you can write differential equation with respect to this parameter. And you would arrive to Painlevé 2. So that's kind of funny thing. So again, so there is all these coincidences. So I consider 2 by 2 problems. I consider so if it is oscillatory and with a regular singularity problems or regular singularity, if it is greater than Poincare 2, or if it is more than 3 regular singularities, I can, first of all, there is no known, at least, contour integral representations, but also there is an extra parameter. If I increase either Poincare index or number of singularities, which I cannot get rid of by scaling and translations. And with respect to this parameter, I can write another equation, and I would get some integrable nonlinear either difference equation or differential. So there is so many, and again, it is good. Although I don't have explicit formulas, but my main thing would be to present some asymptotics, this intermediate asymptotic, in such a way that when x goes to infinity, which means, you remember, x it is a product of n and t. It means t more or less fixed. So n goes to infinity. I have to arrive at the Séguin formula. But when x goes to 0, it means that t goes also to 0 very fast. I have to arrive to Fischer-Hartwig asymptotics. So to be perfect, this scheme I should be able, even though I cannot solve Painlevé 5, I should be able to write connection formulas for Painlevé 5 between 0 and infinity. And I can do it, and this is another story. I can do it again actually using nonlinear steepest descent nowadays for this Riemann-Hilbert problem. So I use steeple descent for my original problem to calculate large n asymptotics. Then I use steepest descent for my original problem to calculate double scaling asymptotics. I arrive to some model problem with the parameter x, which is a double scaling parameter, and I can use this nonlinear steepest descent form to derive connection formulas for solution of this Riemann-Hilbert problem, to be able to indeed to describe the to describe the transition asymptotics. And let me finish giving answers. So let me just exactly describe what is. So I didn't have time to put it in my. So I have this extra. Let me see. Let me try to find it in my. Yeah, somewhere I. Yes. So let me find it for you. Yes. Okay. Now share this. Okay. So this is from our paper. So to describe the answer for, again, this is my asymptotics for, this is my double limit asymptotics for my dn. And let me first introduce in this explicitly this Painlevé 5. So this is a sigma form of Painlevé 5. This is a Painlevé 5 itself. My A, B, C, D, in my case, in terms of my alpha, beta, are given, in this way. So this is the equation. So the answer will be given in terms of solution of this equation. Okay. And solution of this equation, and the answer is this. So logarithm of dn equals, so you see it is a kind of Seguin part. It is a Seguin part. Then there is some kind of linear part of, if t is linear part of n. Then this is the sort of the deformed Widom constant, deformed Seguin constant part. So when t deformed Seguin part, this is a constant which involves g functions, and this is a function omega on 2nt which involves solution. This is a sigma solution of this my Painlevé 5. And which solution I have to take? I have to take solution that behaves as when x goes to plus infinity in this way. There is only one such solution. And at 0, this solution, when for generic, when alpha is not z, it behaves like that. So this is a non-trivial fact, which I can do because I have this Riemann-Hilbert representation for my sigma, for that Riemann-Hilbert problem for Painlevé 5. It is exactly so I know how a solution which behaves like that and plus infinity behaves at 0. And this behavior is exactly what is needed for this formula to become Seguin formula when so when t is fixed and goes to infinity, it means that this thing is go. So this integral kind of goes to its infinity. These logarithmic terms begin to cancel these terms, and if you look carefully on everything, you would indeed get Seguin formula. If instead it goes to 0, if n times t goes to 0, so if t goes to 0, then using this behavior of here, you would recast this formula to Fischer-Hartley formula. So this is yes, it would be good to give details to how to translate this formula. Sorry, I have not prepared it, but nevertheless, this is the answer. This is as best as you get for the transition regime. So this is a for particular choice of alpha beta, alpha 0 beta 1/2. This is going to be what appeared in the case of Ising model, and the first this type of results were obtained in long ago by in this famous series of papers by Baruch, McCoy, Tracy, and Wu, when they kind of first discovered the appearance of the Painlevé 3. Well, Painlevé 3 and Painlevé 5, they are more or less the same in Ising model. But exactly what they did, but using kind of the different and original kind of techniques, they indeed obtain this sort of transition described by Painlevé 5. So this we will get the answer for particular choice of alpha, beta, and V. So this is the okay. Maybe I should stop here.
Thank you.
Everybody, I'm kind of here. Okay.
Again, the first part was very understandable, but about the of course, only some detail.
Yeah, but you see, it is a good marketing. You call your talk kind of Toeplitz, and Painlevé still fancy word. So you attract people, but then you but you don't deliver exactly what you promised.
Yeah, right.
Marketing, good marketing. So that's a technique. Yeah. But yes, this is just, yes, I understand. So the last part was very sketchy. But I hope that, well, what about Fischer-Hartwig? Fischer-Hartwig part.
Yes.
It is
was understandable.
good. I'm glad. Yeah.
Many thanks.
But again, in the very general terms, so about Painlevé. So Painlevé, of course, appears in Toeplitz determinant in random matrices very often. And basically, usually they appears in two ways. In fact, if I take this my last if I take this last symbol which I used to describe the transition, so this one where it is.
We don't see anything.
I know because I stopped sharing to show. Okay, now I will try to
share.
I will try to share it again. Where it is. Yeah. So this symbols. Forget about V. It is this symbol. Then this is algebraic function which has this, and as Volodya said, it was not very understandable what I did with this transition. But if you consider my very original problem for Y with this symbol, and I can undress it exactly in the same way as I did with my last portion. So I can kind of move those singularities remove those singularities from jump matrix to extra regular singularities at point and this point and that point. So I can rewrite my original problem as a problem with the constant matrices, as a constant jump matrices, and with the power singularities at this point and that point and at infinity, z to the n. So I can again go ahead with this differentiation idea, and I would obtain Lax pair for Painlevé 6. So from the very beginning, this determinant, this is a Toeplitz determinant of this weight, it is just the sigma function, so tau function for Painlevé 6, for some particular solution of Painlevé 6. So before any limit in Toeplitz determinant, in random matrices, before any limit taken, you have Painlevé. But those Painlevé are not Painlevé transcendent. They are just special solutions of the corresponding Painlevé equations, which are given by your determinants. So this is from the point of Painlevé equations, Painlevé theory, this is a special classical solutions. And you would not get much more for finite n from this information. Well, differential equation Painlevé 6, yes, so except that you can write some differential equations for your Toeplitz determinant, for fixed n. But the second appearance, it is in this transition limit, when there appears as a model solution at some. So this is what, from the point of view of Painlevé theory, what I tried to do in the last step, it is just the transition, just the limit from Painlevé 6 to Painlevé 5 on the level of some special solutions. So I just recast, I just calculated the limit, some double scaling limit, which brings some special solution of Painlevé 6 to some special solution of Painlevé 5. And this Painlevé 5 is already genuine transcendent. So it is not a classical function. Okay, so this is my kind of probably some extra general remark.
Mhm.
I see, but in order to understand it in all details, it takes a time.
Okay, if you know, if life would be generous to all us, and we will have our program finally set in spring, so maybe we can have some, well, some. I can say I will be able to give some maybe continuation of this mini course.
It's a good idea.
Well, but it would be great to have it in the normal circumstances, because
Yeah,
I see.
I'm afraid it's difficult.
this Zoom, well, even if I learn how to use iPod, I wouldn't say that it would be much better.